This study introduces an innovative method for implementing an advanced RAG system using graph theory and agent-based modeling. The authors aim to create a more efficient and scalable RAG system by leveraging the strengths of both approaches. They begin by explaining the concept of RAG systems, which are designed to analyze and visualize complex systems and networks. However, traditional RAG systems have limitations, such as being unable to handle large-scale networks and lacking adaptability to changing system dynamics. To address these limitations, the authors propose an agent-based approach to RAG systems, where each node in the network is represented as an autonomous agent that interacts with its neighbors to gather information and make decisions. This approach enables the system to adapt to changing network topologies and dynamics in real time. The authors also discuss the implementation details of the proposed system, including the design of the agent architecture and the communication protocols used for agent interaction. They highlight the importance of using a decentralized approach to agent communication, which enables the system to scale more efficiently and adapt to changing network conditions. The authors conclude by highlighting the potential applications of the proposed system, including its use in analyzing and visualizing complex systems and networks in various domains, such as social networks, transportation networks, and biological networks. Overall, this study proposes a novel approach to implementing RAG systems using agent-based modeling and graph theory, which has the potential to overcome the limitations of traditional RAG systems and enable more efficient and scalable analysis and visualization of complex systems and networks. The traditional Retrieval-Augmented Generation (RAG) models have significant limitations, particularly their reliance on previously trained data, which can lead to inaccurate responses. This study aims to improve the traditional RAG model by integrating real-time data and addressing data freshness issues. The research background, objectives, and the structure of the paper are outlined in the introduction. It also reviews the overview of RAG models, advanced RAG approaches, and case studies of existing research improvements. The RAG model is described in the related work section, including its stages such as retrieval and generation, and its implementation flow. The model's stages are crucial for understanding how it processes information and generates responses. The retrieval stage involves searching for relevant documents from a large corpus, while the generation stage uses these documents to generate an appropriate response. However, the model's performance is heavily dependent on the quality and relevance of the retrieved documents. Advanced RAG approaches have been developed to enhance the model's performance, including techniques to improve document retrieval and response generation. These approaches include using more sophisticated retrieval algorithms and incorporating additional context into the generation process. Case studies of existing research improvements provide insights into the effectiveness of these advanced approaches and highlight areas for further improvement. Overall, this study aims to bridge the gap between traditional RAG models and real-time data integration, addressing the limitations of current models and paving the way for more accurate and relevant responses. The implementation flow of a RAG-based generative AI service involves a vector database to store knowledge, consisting of 3 stages: indexing, querying, and post-processing. Vector store configurations can be categorized into 2 types: pre-stored data and dynamic insertion at query time. When using an open LLM for internal knowledge, security is critical, making local LLMs essential. Multiple local LLMs can be employed for tasks like generating database queries or providing domain-specific answers. Advanced RAG methods have been proposed to enhance performance, such as dividing the retrieval process into stages and re-ranking based on relevance. Table 1 outlines methods to enhance RAG performance, including data cleaning, experimenting with index types, and designing base prompts. These methods can be implemented using frameworks like LangChain or Llama Index. The 4th page of the research paper delves into various techniques to enhance the performance of a RAG system. These include data filtering, query routing, re-ranking, query transformations, fine-tuning the embedding model, and utilizing LLM development tools. The paper also reviews advanced RAG approaches such as self-RAG, corrective RAG, and adaptive RAG, which are designed to improve the accuracy and reliability of generated responses. An advanced RAG model is presented, incorporating additional processes after the search stage to enhance response accuracy and consistency. This includes query processing, search, candidate selection, and candidate ranking. These processes aim to refine the output of the RAG system, making it more efficient and effective in generating relevant responses. The advanced RAG model introduces a novel approach to enhancing the accuracy and consistency of responses in question-answering systems. By incorporating an agent into the answer generation process, the model assesses, improves, and retrieves necessary information to generate responses. This agent is a core element in the advanced RAG system. The LangGraph module, built on top of LangChain, facilitates the development of AI agents driven by large language models, LLMs. LangGraph creates essential cyclic graphs, making it a suitable tool for implementing agent-based advanced RAG systems. This study proposes utilizing LangGraph to develop AI agents that can interact with LLMs. The implementation results of the advanced RAG system are presented, showcasing a development environment and practical examples that utilize LangGraph and OpenAI LLM. The system demonstrates improved response accuracy and consistency, highlighting the potential of agent-based advanced RAG systems in enhancing question-answering capabilities. By leveraging LangGraph and LLMs, the advanced RAG model enables the creation of more sophisticated AI agents that can engage in complex conversations. This approach has significant implications for the development of more accurate and informative question-answering systems. The proposed system's implementation involves several key components, including document loading and embedding, storage in ChromaDB, and transformation into retrievers for document content search. The development environment leverages various tools and libraries such as LangChain for orchestration, LangGraph for agent graph workflow, LangSmith for workflow trace, and OpenAI for embedding and language models. The Python development environment is set up using Google Colab. The step-by-step implementation begins with installing basic libraries and setting up API keys. This includes installing LangChain, OpenAI, ChromaDB, and a web search library. API keys for various modules are securely registered in a .env file, as shown in Figure 3. For retriever implementation, internal documents are loaded using PyPDF loader, and the text splitter is adjusted to efficiently maintain context. The split documents are then stored in Chroma Vector Store, embedded using OpenAI embeddings, and converted into retrievers for search purposes, as illustrated in Figure 4. The evaluation of search results involves linking retrieved documents to user questions. If the document contains keywords related to the user's question, it is considered relevant. This process is demonstrated in Figure 5. The system's performance is evaluated based on the relevance of the retrieved documents to the user's question. The relevance of search results is determined by assigning a binary score of yes or no to each query, as shown in Figure 6. This relevance assessment filters out irrelevant searches. A question-answer RAG chain is constructed, similar to traditional RAG systems, to integrate with the AI agent, as depicted in Figure 7. This chain is used to obtain relevant answer results, as illustrated in Figure 8. When an out-of-context question is attempted, the response, RAG does not have relevant information, is received, indicating that the question cannot be answered, as shown in Figure 9. To improve this, the question can be rephrased into a more optimized version for web search, as shown in Figure 10. This process helps obtain better contextual information from the web. For instance, an incomplete question like, "Tell me what is the capital of the country where BTS is located," can be improved to, "What is the capital of South Korea, the country where BTS is from?" The generated answers are then evaluated to determine if they contain hallucinations, as depicted in Figure 11. Finally, the answers are assessed for their utility in solving the question, as shown in Figure 12, and a binary score of yes or no is assigned to indicate whether the answer is useful for solving the question. This process ensures that the AI agent provides accurate and relevant answers to user queries, while also filtering out irrelevant information and detecting potential hallucinations in the generated answers. The paper discusses the implementation of an agent RAG graph for enhancing answer retrieval in a question-answering system. It begins by defining the agent graph state, which consists of a set of messages used to store and represent the state of the agent graph as it passes through various nodes. The nodes in the graph include retrieve, grade_documents, rewrite_query, web_search_add, and generate_answer. The retrieve node graph is implemented to fetch relevant contextual documents from a vector database. This node is crucial for document evaluation, question rewriting, web searching, and answer generation. The LangGraph tool is utilized to build the agent into a graph by placing the agent into relevant nodes and connecting them with defined edges according to the specified workflow. The state graph class is used to define and manage the state-based graph. The provided code sets up the workflow to define the process for retrieving documents or performing other tasks based on the agent's decisions. After the retrieve node, document evaluation, grade_documents, is performed to determine whether to proceed with generate or web_search tasks. This process is used to manage complex decisions and task flows, ultimately compiling the workflow to create an executable application. The generated workflow can be visualized using Ipython display, as shown in Figure 1.6. The agent RAG workflow is designed to improve the accuracy of answers generated from a knowledge base by implementing a multi-stage process. This process involves retrieving relevant documents, grading them for relevance, rewriting the query for better accuracy, conducting a web search if necessary, and finally generating an answer. In the first test, the question, "Tell me the things to consider when choosing a work uniform," was inputted for the document dress code standards. The question was rewritten to, "What are the main factors to consider when choosing a work uniform," to enhance the accuracy of the answer. This rewriting process can be visualized through the streaming of responses to questions, as shown in Figure 18. In the second test, the question, "Tell me what is the capital of the country where BTS is located," was inputted, which is not in the RAG knowledge information. The system determined that a web search was necessary because all vector RAG documents were irrelevant to the question. The incomplete initial question was rewritten to a complete and rewritten question, "What is the capital of South Korea, the country where BTS is from?" and the query was made, resulting in the correct answer, "The capital of South Korea is Seoul." This process can also be visualized through the streaming process, as shown in Figure 19. By tracing the execution using LangSmith, it can be confirmed that the process of generating answers through web search for information not in the RAG knowledge base proceeded according to the designed agent workflow, involving the stages of retrieve, grade_documents, rewrite_query, web_search, and generate_answer, as shown in Figure 20. This study delves into the enhancement of the accuracy of RAG models, particularly focusing on the theoretical background of advanced RAG models. It presents a novel approach through the implementation of a graph-based agent RAG system, which significantly improves RAG performance by addressing the limitations of existing RAG models. The experimental results demonstrate that this system notably enhances the accuracy and relevance of responses to user queries. The utilization of LangGraph's graph technology effectively assesses the reliability of information, contributing to the improvement of information quality through question rewriting and web search optimization. This research provides a crucial foundation for the advancement of RAG-based generative AI services. However, several limitations remain, such as the system's complexity and the need for additional resources for implementation and maintenance. Future research should focus on improving the generalizability of graph-based RAG systems, expanding the system's applicability across various domains, and developing algorithms to enhance real-time data reliability. This page presents a comprehensive list of key terms, concepts, and methodologies used in the research paper. It serves as a reference guide for understanding the technical aspects of the study. The paper focuses on the development of an advanced machine learning model designed to improve predictive accuracy in complex systems. The model leverages a combination of deep learning techniques and traditional statistical methods to achieve this goal. A significant portion of the page is dedicated to explaining the mathematical foundations of the model, including equations and algorithms. These components are crucial for the model's ability to learn from large datasets and make accurate predictions. The authors also discuss several key challenges associated with implementing such a model, including issues related to data quality, model interpretability, and computational resources. They propose various strategies for addressing these challenges, highlighting potential avenues for future research. In addition, the page includes summaries of figures and tables that illustrate the performance of the proposed model compared to existing state-of-the-art models. These visual aids provide valuable insights into the model's strengths and limitations, as well as areas for potential improvement. Overall, this page provides a detailed overview of the technical aspects of the research paper, serving as a valuable resource for researchers and practitioners working in the field of machine learning and predictive modeling.